A very good morning to all. My name is Soumyadip Jana. Today I would like to present my presentation on Photoplethysmograph-based time frequency and machine learning applications on biomedical signal analysis for medical diagnosis. Let's see the contents. We will discuss objectives, research gaps and novelty, introduction, material and methods, result and discussion, validation, conclusions and references. This work demonstrates prediction of different physiological conditions from real-time PPG-based signal using time domain analysis, frequency domain analysis and machine learning models with comparative study of accuracy between different algorithms for best fitted machine learning techniques. Previous studies have shown statistical analysis of PPG data as well as integration of machine learning algorithms for the prediction of different physiological conditions separately. But in our proposed work, statistical data combined with machine learning techniques have been implemented for the prediction of different physiological conditions. Moreover, a hybrid analytical approach has been shown here. So, real-time PPG-based HRV signals have been generated, processed, and extracted for the time domain features, frequency domain features, and nonlinear feature analysis. Correlation and dependency matrices of different time domain indices on mean HRV have been calculated, and most prominent distinctive features have been taken as input attributes for the different classifier models. Binary classification with best suited ML techniques have also been demonstrated with comparative analysis. Methodology adopted in this work has been shown in this slide. The first block shows the hardware implementation using non-invasive PPG sensor, which is further processed using Arduino Atmega 328P microcontroller. The second block depicts data generation and monitoring using a PC. After that, all the data have been collected and prepared for the calculation of different HRV features. All the features have been calculated in the Python platform. After filtering and preparation of training and testing dataset, machine learning algorithms have been trained with this dataset. After that, prediction and evaluation have been accomplished. PPG signals have been collected from a group of more than 30 healthy Indian individuals, both male and female, within the age group of 18 to 35. A total of 300 HRV data are collected from these individuals during 2 months in different days, of which 150 samples are for resting and 150 samples are for working or stressed conditions. The data were collected within a duration of 20 minutes, including 10 minutes of adjustment, 5 minutes of rest, and 5 minutes of physical activity. As a type of physiological test, participants were needed to go upstairs and downstairs for 5 minutes to evaluate HRV under stressed conditions. The distribution of the randomly selected HRV samples in milliseconds for resting and working or stressed samples in box plots have been shown in this figure. The figure represents the range of the HRV samples of different physiological conditions from different age groups and genders. Figure depicts that resting persons have larger variation in their HRV values, while working or stressed persons have less variations in their HRV ranges. This has been found as one of the key features for determining the different physiological conditions. All the different time domain, frequency domain, and nonlinear features have been calculated, shown in the table. In total, 21 number of different features have been considered. This figure shows correlation and dependency matrices of different time domain indices on mean HRV for randomly chosen samples from resting and working or stressed persons of different age groups and genders. It has been observed from the correlation and dependency matrices that the standard deviation SD, standard deviation of the normal to normal intervals SDNN, average peak variability APV, root mean square successive difference RMSSD, and standard deviation of successive differences SDSD show more prominent distinctions between the different physiological conditions. Therefore, for each HRV sample, sex, age, HRV mean, SD, RMSSD, SDSD, ARV, SDNN, PNN50 and PNN20, total of 10 numbers of attributes have been taken as input of the ML classifier. Ultra low frequency and very low frequency power has been obtained from the ultra low frequency and very low frequency power bands from the power spectral density of the RR interval data, which has been shown in the figure. In the left side, the figure shows the power spectral density of the RR interval of a randomly chosen person at different physiological conditions. Less variation in resting subjects and larger variation in working or stressed subjects clearly distinguish different physiological conditions. The right side figure depicts computation of frequency domain features using FFT in the Python platform. The very low frequency VLF and the low frequency LF bands range from 0.0033 to 0.04 Hz or 3.33 to 40 mHz and 0.04 to 0.15 Hz or 40 to 150 mHz respectively. High frequency band ranges from 0.15 to 0.4 Hz or 150 to 400 mHz and the very high frequency band ranges from 0.4 to 0.5 Hz or 400 to 500 mHz respectively. All the frequency domain parameters have been computed using the first Fourier transform of the RR or interbit interval data and obtained the power spectral density by taking the absolute squared values of the FFT coefficients. The PSD represents the distribution of power across different frequency components in the RR interval signal. NumPy library has been used in Python code to perform the FFT and to calculate the PSD. Matplotlib library has also been used to create a frequency spectrum graph from the HRV data. Both these figures show power spectral density in the frequency domain for randomly chosen samples from resting persons and working persons of different age groups and genders. At resting condition, figure depicts less variation and at working or stressed condition, figure depicts more variations in the frequency bands. Poincare plot is a graphical representation of two components of the same signal in a two-dimensional graphical plane. The high continuity of the Poincare plot indicates low disturbances in the signal, which signifies the difference between the consecutive elements is very low. But when discontinuity occurs, the signal generates disturbances in the form of rapid changes in the signal level. Frequency domain indices SD1 and SD2 have been chosen for the Poincare plots. The distribution of SD1 and SD2 values for different physiological conditions is shown in the figure. The left side figure explains high continuity of the Poincare plot, which indicates low disturbance at resting conditions of 4 randomly chosen subjects at different age groups and genders. On the other hand, the right side figure shows discontinuity, which indicates high disturbances at working or stressed conditions of 4 randomly chosen subjects of different age groups and genders. Nonlinear feature analysis has also been done using Shannon entropy. It measures the uncertainty or randomness among interbit interval values. It can be concluded that higher values of entropy indicate greater variability and less predictability in the physiological conditions, while lower values indicate more regularity and predictability in the analysis of different physiological conditions. Five different machine learning algorithms, namely logistic regression, k nearest neighbor, KNN, random forest, support vector machine, SVM, and decision tree have been used. Out of 300 samples, 100 samples for each class, that is a total of 200 samples, have been considered to develop the training method for the different classifier algorithms, whereas separate 50 samples of each class, that is a total of 100 samples, have been used to validate each of the proposed machine learning models. 10 different attributes, as I told earlier, have been taken as input. Therefore, the size of the input vector is 200 into 10. It has been observed from the table the accuracy of the random forest machine learning approach is found to exceed 91%, and the remaining classifier gives the accuracy below 90%. This figure shows all the ROC curves of each ML model. To conclude, it can be said that accurate and efficient techniques by hybridization of different supervised machine learning models and time domain indices for the improved understanding and diagnosis of various physiological and pathological conditions of human beings have been proposed. Frequency domain and nonlinear indices have also been considered. These features produce consistent trends and significant differences during the resting and working or stressed phases. Poincare plot distribution has also been performed to analyze the quadrant. Comparative study of different machine learning algorithms highlight selection of best fitted machine learning techniques for the binary classification of different physiological conditions generated from real-time data. Hence, the real-time simple time frequency feature-based classifier makes the ML models novel and suitable for identifying different medical conditions and states for real-life implementation. These are some of the references which I have taken for my research work. Thank you all for your kind patience.